the last topics of sensor about strain gauge, and also a brief introduction about signal conditioning, if I'm not mistaken. But anyway, I will start and review again about signal conditioning. So the next topic, after you finish with many kinds of sensors, you started with temperature, thermocouple, RTD, then continue with the pressure sensor, level indicator, which I have given you last week. So last week was days off. It's not really holiday, but it's a week off. So I have given you the PowerPoint for you to read and some video for you also to check out. And next week, it was supposed to be a week off again, but there is a change in schedule. There's a schedule change. So next week, we still continue the class. So the exam was organized only last week. Right. So now I will start with the new topics. After finishing all about sensors, now we are coming to the signal conditioning. So from the name signal conditioning, why do we need signal conditioning? If you remember, when you plug in or when you install thermocouple in your system, in the whole system, and the thermocouple will sense or will read the temperature change of, let's say, your furnace, then the results will be in voltage, let's say. But then these signals, this voltage can be very low, can be too much noise, and you don't need it in voltage, but instead you will need it in current, electricity current, or etc. So that we need what we call as signal conditioning. So signal conditioning is an operation performed on the signal to convert it, so to convert the signal to a form suitable for the interface, for interfacing with other elements in the system. Like I said before, from your thermocouple, it sends the temperature and it gives you voltage. Let's say the voltage is too small and it has too much noise, and then you need to filter, you need to remove all the noises, then you need to amplify. So amplify is basically to increase the signals so that the next element, the later elements, can read this signal. So that we need to condition these signals. That's why we call it with the name signal conditioning. So there are many activities, I might call it activities in signal conditioning. It can be signal range or offset changes. For example, amplification, just like what I have given you. So the signal is too low, it's in millivolt, but you need it in voltage, or you need it in kilovoltage, etc. So that we use amplification and zero adjustment. And also conversion is also signal conditioning. From the name conversion, so it means we convert, let's say, the current by using RTD, we get the current, but then we need it in voltage. So you need to convert the signals from current to voltage. or from voltage to current. Depends on the needs. And also filtering. Filtering is to remove all the noises, all the unwanted frequencies. Signal conditioning. Before discussing to the main topic of signal conditioning, we will discuss this one by one. Signal range, conversion, and filtering. We will discuss this today one by one. Before coming to the main topic, it is important to know the following topics. Okay, we need to know first what is the loading effect. What is loading effect? So the loading effect is, let's say if you have the Wheatstone bridge, like I told you a couple of weeks ago, you have the Wheatstone bridge connected to the RTD, then if this RTD doesn't sense anything, any temperature change, so there is no load. But then if this RTD senses the change of temperature from your system, from your furnace, then we may call it as a loading effect. Okay, there's a loading effect, there is a buffer circuit, and there's a difference amplifier, and the instrumentation amplifier. Let's take a look one by one. The effect of loading. Number one, the effect of loading. The measurement systems are made up of many components, right? So, for example, your thermocouple or your strain gauge or any other instrumentation, measurement instrumentations. It is made up of many components. So ideally, the gain of the whole system is found by multiplying the gains of the individual components together. So the whole gain of the system is a result of a multiplication. And point number two, however, this will only give the correct results if very little current flows through the connection circuits. Okay. And next, point number three, in reality, some current flows. This results in a much more complicated expression for determining the gain for the entire measurement system. You know, when you have one element, so you have the gain for each element. Then if you have many elements, you will have a gain for each element that you have to multiply. So this problem is called loading. We use operational amplifier circuits to help stop this loading problem. So if you use many elements, each element has gain, then you have to multiply gain from each element, then it adds load. So this is what we call the loading, the effect of loading. Let's see here the effect of loading, the loading effect. The connecting a sensor or circuit to load introduces uncertainty in the measurement. So that in the amplitude of the output voltage as shown below. Okay, so here there is no loading effect. So the output voltage and the input voltage will be equal. So Vy equals to Vx without the loading. And then if there is a loading, then the output voltage or the input voltage might be lower than the output voltage. The output voltage, the Vy, so the output voltage here, this is our output voltage, and this is the source, the input voltage. The source of the sensor can be found by using this equation. So Vy equals to Vx. 1 minus this, you can find it in the book. The book I have told you, the Curtis Johnson book. So the output voltage is reduced by the voltage drop over the internal resistance of the sensor Rx. Number 3, to reduce the uncertainty, therefore to keep VW as close as possible. So we cannot keep it exactly the same, but we can keep it as close as possible, Vy close to Vx. The internal resistance, the sensor output resistance, should be much smaller than the load resistance. So let's take an example. Example number 1. Here we have an amplifier. Okay, so remember amplifier? From the name amplifier, it is used to amplify. What is amplify? Well, you can take a look in the dictionary, the word amplify. So an amplifier outputs a voltage that is 10 times the input voltage. Okay, let's read the first line. And then it has an input resistance. So the input resistance is 10 kilo ohm. A sensor outputs a voltage proportional to temperature with a transfer function of 20 millivolt per degree Celsius. Okay, so we know that this is a temperature sensor. The sensor has an output resistance of 5 kilo ohm. If the temperature is 50 degrees, find the amplifier output. Okay, we know the input, and we want to find what is the input voltage and what will be the output voltage. And we know that the clue is the output voltage will be 10 times higher than the input voltage. Okay, now if we draw the diagram, it would be this simple. Okay, so this is the simplest diagram. We have the sensor. This is the sensor, right? And the sensor, it has a sensor outputs a voltage proportional to temperature. So it has what I call as an rate, the change of volt per degree Celsius. So this sensor has properties 20 millivolt per degree Celsius. Okay, and it sends the temperature. So this is the temperature. It sends the temperature, and the sensor, the temperature sensor, it has the properties of 20 millivolt per degree Celsius, and then it converts it into voltage. This voltage is coming to the amplifier. So this triangle symbol is amplifier. You should keep that in mind. Then this amplifier has gain equal to 10, because we know that it will multiply, it will amplify the input voltage 10 times to become the output voltage. Okay. And now if we break down again, if we draw the diagram in more specific design, you can draw it like this. So we have the voltage, the Vt is coming from the sensor, and we know that the output resistance of the sensor is 5 kilo ohm. It is known before, and also for the gain, for the amplifier, it has 10 kilo ohm. what we call as input resistance. Then how can we solve the problem? So we can do it one by one. First, we should find what is VT, the output voltage from the sensor. So the output voltage is 20 millivolt per degree Celsius times the temperature sensed from the system, 50 degrees Celsius. So it is equal to 1 volt, right? And how about the output voltage? So here you have 3 voltages. So keep that in mind. You have 3 voltages. Let's go back to the diagram. So you have the voltage produced by the sensor, which we call it as a VT. Then this VT will be transferred to the amplifier as a V in, then this V in will be amplified to be the V out. So you have 3 voltages that you should remember. And the V out, we know it, V out should be 10 times higher than the V input. I think this is enough. So it means we need to find what is V input that is coming to the amplifier. So the V input is equal to VT. This is the formula before, 1 minus the resistance of the sensor and the resistance of the amplifier. So from this formula, you can get V input coming to the amplifier, 0.67. And then now you can see what is the output voltage. It's 10 times from the input, which is 6.7. Okay. So before it is too small, so this signal is too small, 0.67 volt. It's too small to be read, to be, let's say, you want to use these signals for a later process, but then 0.67 volt is too small, which means you need to amplify it, you need to make it bigger so that it becomes 6.7 volt. All right, that is the loading effect. You can see that there is the effect from the amplifier, and there is the effect from the sensor as well. If you have many elements in the system, you will have to multiply gain from each element. Okay, now let's continue with the buffer circuit. Okay, remember there are 4 things that we should learn before coming to the actual signal conditioning. So the buffer circuit, it aims to minimize the loading effect. So we must look for a circuit that has a very large input impedance to obtain the whole sensor output voltage. So if we want to minimize the loading effect, we have to find circuit having very large input impedance. So about impedance and filtering, we will learn about this in the next meeting. And point number 2, as this circuit is probably going to drive other circuits, it should have very small output impedance. So it should have large input impedance, but very small output impedance. A device having these 2 properties is called a buffer. I believe you heard buffer very often. So this is actually buffer. So we'll have a very large input impedance, but very small output impedance. So one example of buffer is the voltage follower. Here is a symbol. You'll learn this probably on Wednesday next week. We'll learn more specific about operational amplifier. Then you will learn what is the symbol and why it is connected to the minus but not the plus, and etc. This is an introduction that you need to know before coming to the main topic of signal conditioning. And difference amplifier in signal conditioning, it is sometimes required to find the difference between two signals, right? So this is specific in signal conditioning, specific for amplifier. Like in the previous example, we want to amplify the voltage. We need to find the difference. You know the difference? The difference is delta. The difference means delta here in mathematics. So this can be achieved using the following difference amplifier circuit. I will not discuss this in more detail. This will be in the topics of operational amplifier. But the thing is, we need to find this V2 minus V1. This is what we call as a difference amplifier, V2 minus V1. Okay, now we are coming to the main topic about signal conditioning. Signal conditioning, as I mentioned in the previous this meeting, in the previous slides of this meeting, the examples of signal conditioning can be number one, signal range and offset changes. For example, amplification and zero adjustment. From the name zero adjustment, so you adjust the place of the zero. And also it can be conversions. You want to convert from voltage to current or current to voltage. It depends on your requirements of your system. And also filtering. Filtering aims to remove the unwanted frequencies, or what we call as a noise. Let's see number one, signal range and offset or bias. Let's take a look at an example. So design a circuit to achieve the following voltage conversion. Right, so this is another example. So you have a voltage coming in and it's too small. It's 0.2 up to 0.7 volt. It's too small, right? And then you want to get about 0 up to 5 volts. So you need a signal conditioning circuit here. You need to design how can we amplify the range, the signal range from this into this. Right, so it is clear that we need to subtract 0.2, then multiply the signal by 10. Right, so it is clear that from 0.2 to 0.7, the difference is 5 times, right? 0.5. So we can shift 0.2 into 0, and we can also shift 0.7 into 0.5. So they will have the same range, right? Here we have the same range between 0.2 to 0.7 and 0.0 to 0.5. Right. After you shift to 0, it will be easier. Now to amplify this to be 5 volts, right? So you have the same starting point, 0 volts. Now we need to amplify this to be 5 volts. This looks like, let's read this point number 2. This looks like a differential amplifier with a gain of 10 and a fixed input of 0.2 volts to the inverting side. The following circuit shows how this could be done using an instrumentation amplifier. So what can we see here? This is 10 times, right? So this, we did an amplifier which has gain of 10 times because from 0.5 to be 5 volts. Okay, now let's see example number 3 again. A sensor, let's take a look at example number 3. A sensor outputs a voltage in the range 20 to 250 millivolts. Okay, here pay attention to the units and develop a signal conditioning so that this becomes 0 to 5 volts. The circuit must have very high input impedance. Let's see linear equations. I think this is the simplest approach. Let's develop a linear equation for the output in terms of the input. So V out, you remember this equation? This is actually a line equation, very simple. So V out equal to A constant, V in plus B. So we need to find A and B. Now let's plug in to the actual value. What is the range? The range is from 20 up to 250 millivolts. So it means 0.2 up to 2.5, isn't it? 0.02, 20 millivolts, it becomes 0.02. 250 millivolts, it becomes 0.25 volts. Okay, so we match between the lower bound to the lower bound and upper bound to the upper bound. Then we put it here, 0 equal to A times 0.02 volts plus B, and you have 5 equal to, this is the upper bound, the upper limit, A times 0.25 plus B. Because we have two equations with two constant, A and B, we can solve and find the value of A and also find the value of B. So it means you can see the relation between the output voltage and the input voltage follows these equations. Right? If the previous example, V out is equal to 10 times V in, it's simple. But now if the range is unpredictable like this, if the range from the input is quite unpredictable, it doesn't have the same range as the output voltage, how can we find the relation between the output and the input voltage? Here is one example by using linear equations. So here is the relation. So it means your amplifier should be able to amplify the input voltage by following these equations. Okay, V out equal to 21.7 V in minus this. Okay, now let's continue with the conversion. That was signal range and amplifications. It shows you how to amplify. This is quite easy. So this is 10 times from the input, but if the range is not that easy, then you need to use this line equation, linear equations. It's the simplest equations in mathematics. Let's continue to the second types of signal conditioning. The second types of signal conditioning is conversion. From the name, let's read point number 1. From the name, in many situations, it is required to convert one form of signal or physical value into another form, such as resistance to voltage, voltage to current, or current to voltage. It really depends on the users. So for example, a typical standard in process control system. What is process control system? Do you know the process industry? The process industry is like petrochemical industry. Petrochemical industry is also process. They use a very big evaporator. They use a cooler and etc. So we call it as a process industry. So in the process control system is to use current signals in the range 4 to 20 milliampere for transmission. So this requires conversion from voltage to current at the sending end and a conversion from current to voltage at the receiving end. So it really depends on the users. If the current signals is in if the current signals is in the input and you want it to be voltage at the other end of the output, so you need to convert it. So here's one example of the current voltage converter. You will see this symbol quite a lot. This is basically amplifier, what we call as amplifier symbol, but it can be used for not only for amplification, but it can also be used for conversion. So here is our input current signal. Then you wanted to get in the voltage. Okay, so the output voltage is equal to minus the resistance coming from here, connected to the inverter, then times multiply to the current signal. Okay, don't worry about this. We'll go into more detail and use more examples to understand. The next type of signal conditioning is filtering and impedance matching. Two other common signals conditioning requirements are filtering and matching impedance. Often spurious signals of, let's read this, number 1. Two other common signal conditioning requirements are filtering. We need to filter the signals. The same as, I don't know, let's say when you bug someone, do you know bugging? Bugging means it will be in the old era. So, for example, I want to hear. So I'm from police department, and I want to hear the conversation of the corruptors, let's say, or we want to listen at the conversation between the criminal suspects. So we bug their telephones. You know these words, right? Bugging. So we get the signals, we get the conversation, but it's too noise, too many frequencies coming into the conversations. Let's say we bug the telephone at home, but the conversation is between someone outside and someone at home. So someone outside, there can be noises from vehicles, can be noises from many external environments. So we want to get rid of that so we can get the very clear human voice conversation. So this is one example of filtering. This is also signal conditioning. Okay, number two, often spurious signals of considerable strength are present in the industrial environment, such as the 50-60 Hertz line frequency signals. Okay, this is like what I told you before. In industrial environment, there can be a considerable strength of signal. In many cases, it is necessary to use high pass, low pass, or notch filters to eliminate unwanted signals from the loop. And one and all, the filtering. Here, I divided into several branches. So filtering and impedance matching tool to filtering and impedance matching. There can be two circuits. Okay, there can be active and there can be passive. So in the active circuit, you have a gain and feedback. In the passive circuit, you have divider circuits, bridge circuits, and RC circuits. Okay, and this RC, you will have low pass, high pass, band pass, band reject, and so on. We will learn this in more detail. Okay, in passive circuit, I will give you a brief introduction to passive circuit. In passive circuit, a passive circuit is composed of a resistor, inductor, and capacitor. And it is used to eliminate unwanted frequency. It can be low or high frequency, okay, without changing any signal that are coming to the system. So here is the passive circuit. Again, if you remember the previous classifications, so the passive circuit, now we are focusing on the passive circuit. You will have divider circuits, bridge circuits, and also the RC circuits, RC filters. And we'll continue with the passive circuits in the next meeting on Monday. But I want to show you, you can find the informations that I have just given you in the book. Okay, this is the book that we are using during this course. Signal conditioning will be in page, here is page 60. Yeah, you can see it in the screen. Signal conditioning, page 55, sorry. So you can read in more details I cannot cover everything. Well, you are not in elementary schools, so I will take only the main point from the book. Uh, any more, if you want complete information, you have to read it. What I like about university is the students should be independent. Okay. And here, signal level and bias changes. This is what we solved previously. This is one type of signal conditioning. And another type that I haven't explained yet is about linearization. You can read it. What is linearization and why we need linearization? Well, from the name, you can guess that the input signals can be nonlinear, can be highly nonlinear. And then for next calculation, let's say you want to calculate this change temperature change from the thermocouple. So to ease the problem, you want to linearize. So from here, nonlinear signals into linear signals. This is also one type of signal conditioning, linearization. Very easy language. I think it's easy for you to understand. The circuits. I'm not jumping into the circuits yet. I'm giving you brief introductions, types of signal conditioning. Conversions, this is what we've learned again, to convert from voltage to current or from current to voltage. There's a signal transmission, and also there's a digital interface and so on. And filtering and impedance, right? This is we will continue this on Monday, filtering and impedance. This is very important. There is a passive circuit and also active circuit. We will continue on Monday with the passive circuits. And concept of loading. We have learned about this. You can take a look here. Here is the formula that you will use, and how to find the loading, the amplification from the output, to find the output from the input if there is loading from the sensor and from the gain itself. Okay, so here's what we call as a concept of loading. We have load here, so it means we need to consider this in order to find the output voltage. Right, so on Monday, we'll continue with the passive circuits. Here's a passive circuits. There are many types, divider circuits. I will encourage you to read this before the class. Here's the divider circuits and many other circuits. We'll get into in more details next week, Monday, and bridge circuits as well. Okay, I will share again the code for attendance here in the chat group. I will encourage you to come exactly at 1 and at the latest, or on Monday if it starts at 4, I will encourage you to come exactly at 4 or at the latest 4:10, not more than 10 minutes. Okay, because for you who are coming more than 10 minutes, I will not admit it into this class because I'm concentrating in my PowerPoint, and every time I have to admit student one by one, and I will not do that anymore. So I will encourage you tops 10 or 15 minutes. Okay, 15 minutes is fine. All right, that's it for today. See you again on Monday. On Monday, actually, we'll learn even more serious topics about circuits. We learn on Monday about the divider and the bridge circuits and so on. Is there any questions?
Yes, ma'am.
Yes?
May we have today's slide, ma'am?
You want the slide?
Yes, if
Okay, I will share probably on Monday. I will combine with Monday's topic as well.
Thank you very much, ma'am.
All right, thanks for coming, everyone. See you again on Monday at 4. And as I told you, it's also in the books, so you can read it first. Then you'll catch up on Monday. Goodbye. See you.
All right, ma'am.
Thank you, ma'am.
Happy fasting, ma'am.